Hi all, and welcome to the Medical AI Lab session. Today I'm delighted that we have Sina Hartung present on Reliable, a library associated with a paper that got Best Paper Award or Outstanding Paper Award at NeurIPS 2021. So without further ado, I'll hand it off to you. Sina, take it away.
Thanks, Pranav, and welcome everyone. Super excited you're here. Yeah, today we're talking about deep reinforcement learning at the edge of the statistical precipice. Pranav, help me here.
Precipice is how I would pronounce it.
Precipice, yeah, I'm sorry. That's the paper. Like you said, it won Outstanding Paper Award at NeurIPS 21. And there's also a GitHub repo associated with it that sort of provides you with a Python library to use the tools that they introduced in this paper, which are really exciting, and we're going to talk about them today. So I just want to briefly walk through the paper, sort of why the paper came about, and then dive into some of the methods as they're applicable to our research. So just a super brief recap. Reinforcement learning, we're trying to learn optimal policy to maximize a return while we're sort of interacting with an environment. That's sort of been very popular in playing games, and we've seen some of these models being really good at things like AlphaGo. So generally, we're sort of learning from experiences to make decisions, and that's obviously also really relevant for medical decision making. And so currently, the standard for evaluation often focuses on point estimates. And so the paper sort of highlights specific shortcomings of that evaluation and how they would improve upon that. And so currently, the authors argue that the evaluation is not reliable, especially with sort of the few runs that are currently being used to evaluate these models. That comes from computational constraints and sort of with the development of the arcade learning environment, that's sort of a framework that allows AI development for Atari games. That's been sort of the number of runs that people use on their models sort of declined over the years. And so there's inherently just a variability in performance of these deep RL algorithms, but couple that with sort of the small and few runs for the models, we have a statistical uncertainty that comes in, especially when we look at point estimates. And so theoretically, you could say like, okay, so like if we just repeat, and we have more and more runs, like could we get rid of a big part of that uncertainty? And theoretically, that's true. That's just not computationally feasible. So the reason why we have fewer runs is because oftentimes it's sort of computationally prohibited to sort of go above a certain number of runs, just because you would run like hundreds and thousands of days if you do on the 200 million Atari with like 50 games or so. So that's sort of not feasible to do. And another point that they're making is that the way currently evaluations work, they're very not easy to reproduce. And therefore, they're sort of introducing this framework to make these evaluations more reliable and generally in terms of uncertainty, but also make them reproducible generally in the RL community. And so they're proposing the tools in the paper and have an associated Python library. And what they're proposing is they're saying that the estimates are a random variable, and therefore we should treat them as such. And so there is a few methods that are proposing: stratified bootstrap confidence intervals, performance profiles, which I really like because I think they give a really good overview over the general performance, and we'll see that later, and sort of different aggregate metrics over mean and median. And here specifically, they talk about the interquartile mean and the optimality gap that I really like sort of as an improvement upon these two. And I'm seeing that there were questions in the chat, but I hope everyone can hear me hear me well? So the authors have tweeted about this, as is common. And there's a too long, didn't read, and so that actually I really liked. Our findings call for a change in how we evaluate performance on deep RL benchmarks, for which we present more reliable protocols, easily applicable with even a handful of runs to run unreliable results from stagnating the field. And so I think this really, summarizes the paper pretty well. And so let's run through one of the case studies that they're doing to kind of show what's currently wrong with what's happening, and then walk through some of the code and methods that proposed together. So they look at a few methods, but specifically they do a reevaluation of the Atari 100K benchmark. And what that is basically we're looking at 100K interactions for the training. So that's 2 to 3 hours of gameplay. And we're looking, or they're specifically looking at 26 of the Atari games. And then they're looking at the medium human normalized scores. So usually they do that for 5 different algorithms, and they sort of go with the runs that are used in the papers of these algorithms. Usually these are 3 to 5 runs per games, very rarely 10 to 20, but rarely. And that's sort of the setup that they have. And they find substantial discrepancies sort of between the conclusions that are drawn from the point estimates alone versus a more thorough statistical analysis that they're performing with their methods. And so we have 100 independent runs for each of the algorithms. And so one run is like training one algorithm on each of like the 26 games. And then for every one, we have a score, and that score is the average returns from 100 evaluations of episodes. And so we have 100 times 26 scores per algorithm, and we subsample with replacement. And so that sort of gives us a distribution of point estimates, and we're comparing that, or the authors compare that to sort of the point estimates given in the papers. And I think that's sort of the first eye-opening, interesting graphic that they provide is this one. So the median may lead to wrong conclusions. And so we're seeing different distributions here, and the distributions correspond to these different medians that they basically calculated with just resampling. And we see the different algorithms here. So DER, OTR, curl, DRQ, 2 variations here, and SPR. And there's a few interesting things I want to point out here. So first off, we can sort of see that the horizontal, not the vertical, sorry, the vertical lines here, they're the point estimate medians reported in the papers for each of these algorithms. And so if we look to the left, sort of the pink algorithm, curl, we see that the distribution is far, far more left than the actual point estimate that's reported in the paper. And we can sort of see that for DRQ as well. And sort of some of these just don't really match up with sort of what you would expect from the just looking at the distributions. And so one thing that the authors point out here that I thought was interesting is when we look at DER compared to OTR. So DER is blue here, and we're seeing the blue distribution, and we're sort of seeing the blue median that's sort of to the left of the, well, it's the leftmost median, right? So it's the lowest point estimate, basically. And OTR is our left orangey, well, there's 2 oranges, but the left one, the left orange distribution. And we see that the median for that is actually higher than that of DER. But if we look at the distributions, we actually see that the DER distribution is further right to the OTR distribution. And so it sort of seems that this might be a wrong conclusion, where just looking at the point estimate doesn't actually give you the correct ordering. And here it actually suggests that DER might be, preferable or performing better than OTR. And so I think this is an interesting finding, and really speaks to sort of what they're wanting to do with their paper. And so in a next graphic, what they're showing is that we see on the x-axis the number of runs for these different algorithms and sort of how the expected median changes sort of with these runs. And we see that this is very inconsistent, and especially with the ERQ and SPR, we sort of see there's a lot of change here happening. Well, I mean, I guess across the board, but this is really just to drive the point home. What they also do, what I thought was really interesting, is that they look at protocol changes. So for different algorithms, sometimes evaluation protocols change. So this is sort of an inconsistency, you know, across papers, and they're arguing that you can't actually compare across protocol changes. So what they're doing here is they're saying Curl and Sunrise use different protocols in their evaluation. And what they're now doing is they're looking at DER within the original proposed evaluation protocol DER, as well as within the protocols of Curl and Sunrise. And what we're seeing is that consistently just the same algorithm basically performs better on the Curl protocol and then performs even better on the Sunrise protocol. And so what we're basically seeing here is that performance improvements might come from an underlying protocol change rather than an actual improvement within the underlying model or algorithm. And I thought that was actually really interesting as well, because the bigger point here is that this is actually not comparable across papers and across models, and that might sort of weaken the general trust within the field and in these methods. And so I think this sort of drives the point home that you want to have a framework and a way to, across all different methods, evaluate and be sure that you're doing the same thing and that it's comparable. And so the paper is suggesting the following methods. So what they're not suggesting is saying we're fixing a random seed, because why that one random seed? Also, there's sort of randomness that comes from GPU and other sort of hardware side things that sort of would still influence reproducibility and uncertainty. And more runs, as we discussed earlier, aren't feasible. And statistical tests are just by nature sort of dichotomous. So basically saying like it's either statistically significant or not. And that's not really like the best applicable metric for this field, and sort of for evaluating if it's sort of actionably statistically significant, they're arguing. And while they sort of reason from a statistical point of view, they're saying that statistical tests aren't the way to go, which I think is a very reasonable thing to say. Instead, they're suggesting the following things. And all of these are implemented in the Python library, as we'll see shortly. So as an improvement over the point estimates, they're suggesting stratified bootstrap confidence intervals. And as an improvement over sort of these like super big tables with like every single task with sort of like every single algorithm, like just like the means reported, oftentimes they also omit standard deviation. They're saying, well, if you want to get a bird's eye view, we should look at performance profiles, very similar to sort of performance benchmarking as is used in sort of software engineering. And finally, they're saying there's aggregate metrics that are of improvement over mean and median, such as IQM or the probability of improvement or the optimality gap. So let me switch super quickly to here. Yeah, so what we want to look at first is sort of how we can go from these like point estimates, median and mean, to sort of something better that's IQM or optimality gap. And so the argument here is that IQM, it has a lot less, has a lot smaller confidence interval. So it's sort of preferable over the median. It's not influenced by outliers as much. And so for the mean, we have this optimality gap, which basically is compared to a threshold, how much away are you from that optimal threshold, basically. And so the smaller the metric here, the better. And there's actually another graphic that they have that sort of drives this home, is the sort of the optimality gap. And we're saying sort of like human performance is at 1, is a score of 1. And so sort of the smaller this is, the better you're performing. Okay, but let's take a step back and be like, okay, before we look at these point estimates and sort of look at specific performance, we just want to evaluate how the thing is doing, just get like a feeling for these different algorithms sort of across these different tasks. And I think what they're doing great is sort of performing this bird's eye view here. That's sort of the performance profiles that gives you sort of the score with like the score distribution. And so there's a few things I want to point out here. First off, this is sort of a very aggregated view. So we're looking across all of the runs, across all of the games, across these different algorithms. And so for each algorithm, we're looking at how many scores for all of the games do we have with a score that's bigger than some threshold. Yeah. And so this really here is a fraction. So for here, we have like with a score of, you know, between 0 and 0.25, we almost like all of them sort of are within that fraction. And as we get a higher and higher score, sort of compared to a human normalized score, we're sort of going down. And so immediately, the thing you can see here is that this orange algorithm, the OTR, is performing worse than SBR. So that's sort of the main takeaway, is that sort of the further up your curve is, the better you're doing. And I think that's a really important sort of initial takeaway that sort of zooms out, gives you a global perspective, like across all the games, across all the runs, like you're just doing better with the one over the other. And so that's one thing that you can see here. What you can also see is sort of the median here. So at this like 0.5, you can sort of see these like individual point estimates. And that is sort of where you then want to come in with these like more in detail views, right, that we already saw, where you want to zoom into some of these. And there's some inconsistencies where maybe curves sort of overlap for a certain point, but not others. And so really zooming back in then, well, if you see inconsistencies across point-based metrics, these bird's eye views usually allow you to sort of figure out maybe what's going on, which I think is really, really useful here. There is one final thing that I want to point out here. There is also the probability of improvement, which I think is really interesting. And so what they're saying here is that with these algorithms, sort of how certain are we that algorithms are actually improving over this like comparable algorithm here? And I think so we can be fairly certain here, but not so certain here. And I think that's sort of a really interesting way to look at these graphs. And just generally, if we look at the GitHub repo, this is really nicely implemented. You sort of have these metrics that you can sort of just load and that you can then run. And if we look at the code, it's actually really nicely done. Here, for example, so for the performance profiles, we basically just create performance profiles, and we sort of give it our scores and sort of our comparison that we want to threshold towards, and it sort of spits out what we have right here, which I think is very, very convenient. So this is, I think, really applicable to the research that we might be doing. And it's very, very easily usable, which I really like. Yeah, and so I will drop 2 links in the chat for later, but there's a ton more of information on their page. So they actually have 2 blog entries where they like step-by-step sort of go through the bootstrapping procedure, which I thought was really interesting and helpful sort of to understand a little bit deeper sort of what's going on and how they're aggregating into like a global perspective. Furthermore, there's also a presentation by the actual authors from NeurIPS that's available as a video. So if you want to sort of dig deeper, I highly recommend that. I didn't want to just present to you what they presented, so I sort of glanced over some of the things I figured weren't as interesting to us. But there's a ton more that they're sort of doing and showing in the paper, and so highly recommend to check that out if you're interested. That's it from me.
Awesome. Thanks a lot, Sina, for the fantastic presentation. It seems like a very useful tool for us.